My name is Michał, and I would like to show you our project called Object Migration Oracle. So this is a joint project with Onur and Saji. So blockchain is great, but has some severe performance limitations. Currently, Ethereum processes only about 14 transactions per second, which is not enough. This is because all the transactions must be verified by every single miner in the network. This is why recently sharding was proposed. So in sharding, the blockchain is split into groups called shards, and each shard holds a subset of accounts and has its own miners. As a result, we can process transactions in parallel, and theoretically, we can scale up Ethereum almost infinitely, which is great. However, it works like this only if all the accounts being involved in the transactions are in the same shard. If Alice in shard 1 sends Bob in shard 4 a transaction, both shards have to process the transactions and agree with each other. With smart contracts, multiple accounts spread across multiple shards can be involved in a single transaction. And processing such transactions is expensive and can reduce all the benefits we get from sharding. Our project is a solution to this problem. OMO observes interactions between accounts in Ethereum and then places frequently interacting accounts in the same shard. As a result, we can significantly reduce the number of costly cross-shard interactions. At the same time, OMO tries to ensure equal load across shards so that each shard is fully utilized and utilizes all the available capacity. Within this project, we have built a data extraction tool and a Python simulator that evaluates the approach. Also, we have evaluated its performance using ChainSpace, a sharded UTXO blockchain. I just wanted to quickly show you how our project works. So here I have an open Ethereum client running on my machine. I can now launch our script, which basically connects via IPC and try to extract all the information about transactions. And then it produces a simple CSV file, which extracts the block number from a 2. This is from the transaction, but more importantly, it also extracts all the affected accounts from Ethereum EVM. So here we can see that there is a sample transaction in this block coming from this account to this account. But however, there are still quite a lot of accounts being involved by this transaction. And if you have a look at Etherscan, we can see that this is actually a call to a smart contract, and that's why it modifies multiple accounts. Having this file, we can then replay the whole history of Ethereum on our simulator and to see what would be the impact of sharding. I'm not going to show it like this because it's going to take a lot of time. But after the simulations are ready, we can just plot some results. And here, for instance, we can see what will be the impact. So how many blocks we will need to replay the whole history of Ethereum on a sharded environment. And you can see that the current Ethereum approach, which is just randomly placing the accounts, would need much more blocks than our approach. So in this case, 3 or 4 times more. And the simulations are great, but we wanted also to see if this approach works in the real world. So what we did, we are using ChainSpace, which is a sharded UTXO blockchain, and we replay the history from Ethereum on ChainSpace. So we had scripts to launch a lot of instances, which will act as miners, put them in different shards, and then replay the whole transaction of Ethereum and to show what the impact going to be. I cannot show you the full results because we don't have time, but I'm happy to show you, to answer any questions, and all the results are available on GitHub.